Foundation Research Award in 2021. Humboldt Research Fellowship for Experienced Researchers in 2020. Then Fellow of Royal Society of Chemistry in 2019. INSA Award in 2014. And there are many. Now, he is in the editorial, he has several editorial appointments. Just to mention again, if you, this year, 2024, he became the editor-in-chief of SINLET. It's a very popular journal of THEMA. He is also associate editor of Journal of Organic Chemistry. And he is serving several advisory boards, starting from CHEM. You know, this is a very leading journal. And then Chemical Science, Chemistry European Journal, Advanced Synthesis and Catalysis, Organometallics, Chemistry and Asian Journals, Catalysis Science and Technology, and there are many other journals. He has 17 patents in his credit and close to 300 publications with more than 17,000 citation and H-index of 77. He has edited many book chapters and many books and several guest editing of issues in journal publications. So with this brief introduction, as I said, there are a lot to talk about him. I think we are all excited to listen to him with his great science outcomes. So I request Professor Maiti to come on stage and deliver his lecture.
Good evening, everyone. Can you hear me at the back? Right, great. Thank you, Professor Ghosh, for that sweet and kind introduction. I think I'm truly honored, very happy and privileged to be here. Thank you, Garima, for perfectly organizing it. Thanks all my colleagues, dear friends, collaborators, and all the people who I have not been having the opportunity to meet before and got this wonderful opportunity to see here. And I also got some great opportunity to interact some of the students. It has been a full, packed, enjoyable day. I would not like to change at all. I would like to live this life again and again, every day if it is like this. I think it's worth living. So I truly am, again, honored, touched by your humility and the kind hospitality that you have extended throughout my stay and also, of course, throughout the scientific journey before and hopefully coming forward or going forward. So thank you again, everyone, for coming. Thanks for your kind attention. Thanks for giving me this wonderful place to hopefully show and share some of the ongoing research work in our laboratory at IIT Bombay. As Subrata, if you allow me to say, kindly mentioned that we are working in a few different areas. One of the major domains that we try to work is the synthetic methodology development. Essentially, we are, you can say synthetic methodologist, inorganic chemist, organic chemist, organometallic chemist, catalysis, so whatever it means, okay. I'll try to discuss some of the topics that we have been involved in recent past. Okay, let me see. Well, if you have ever seen some of the work that we are trying to do over the last 13 years or so, you may have come across this carbon-hydrogen bond activation. It's a familiar topic, right? We have great colleague and friend, Professor Amit Power is doing wonderful chemistry, and of course Bhaskar is my friend, colleague, as well as collaborator. We are working in quite a lot of domain together. This field has exploded, so to speak, over the last 2-3 decades, right? We take an aromatic substrate or an aliphatic substrate, essentially every organic substrate, and you see there are carbon-hydrogen bond. By definition, organic molecules are made of carbon-hydrogen bond. But we have been told that in our undergraduate studies, functionalizing a carbon-hydrogen bond at only few positions are possible. For example, I'm just talking about functionalization. Let's say Friedel-Crafts reaction, Friedel-Crafts acylation or alkylation reaction. We have been taught, let's say if you have an electron-rich arene, you tend to get at the ortho position or the para position, sometimes mixture between ortho and para depending on the substituent. Right, but how to do a Friedel-Crafts reaction, let's say at the meta position? Friedel-Crafts type of reaction at the meta position. On the other hand, let's say you want to do a nitration of a benzene ring, you can achieve the nitration at a desired position at one position. But there are other positions in the benzene ring, for example. How to do nitration at those positions? This is essentially becomes a challenge. Of course, if at the cost of carbon-hydrogen bond, if you are introducing a new group, that's what is going to give you, let's say, synthesis of pharma molecule, agromolecule, perfume, whatever you want, materials of your interest. But it is never going to be straightforward. As I said, our textbook says that only few positions becomes available depending on the reaction mechanism, and overriding those selectivity is really, really challenging, I would say impossible. And this is where, when things are organically not working out, inorganically, so to speak, if you are able to put the metal at any of those positions where you want functionalization, then people like us can come in, organometallic chemists can come in and try to do the functionalization at those positions. Right? So let's say Friedel-Crafts reaction at the meta position can we do? So I would say yes, you can perhaps do it if you have a metal, right, placed at the meta position. Okay, so this is particularly where we started working on how to put the metal at a position of our choice. For instance, if we want to put the metal at this position, okay, any one of these ligand you can take, let's say this one you are taking, if you are attaching this ligand with the organic substrate, of course that's the limitation. You have to attach this ligand, any of these ligand with the organic substrate, then this ligand by having this, let's say, heteroatom will hold the metal and will deliver at this position. And this positional selectivity can only be achieved in presence of this sort of ligand. If you are interested in placing the metal at this position, so-called, let's say, 4 or para position, you can perhaps then take one of these ligand. Let's say if you are attaching one of these ligand, then you would be able to place the metal selectively at the para position. This has been something we are doing over the last, let's say, 10 years or so. 9-10 years we have been doing. I'll keep it very short. What essentially we are trying to do is, as I said, with the organic substrate that is black in color, we are attaching this ligand that is brown in color. This whole part is ligand. The metal is associated or attached with this ligand, and it is getting delivered precisely at this meta position. So this is like almost demand and supply or the target oriented delivery. You order a pizza, it is at your doorstep. Okay? You order through Amazon, you receive your toothpaste. This is what I think the students are doing. I'm getting delivery of toothpaste in my laboratory every day, or whatever else they are doing. So essentially this is what we are trying to do. You take the organic substrate, you attach the ligand, the brown color, and the metal comes in, and then it activates and places the metal at a desired position. Now the overall design is such that metal will not be placed at the ortho position or para position by utilizing this ligand. Another important thing is that in these cases, we really want a monodentate ligand. Why is that? That is particularly due to the fact that we are using metals such as palladium, and those of us who are reading the metal chemistry, we know that palladium is 2+ usually for carbon-hydrogen bond activation step, and this 2+ palladium would prefer to have a square planar geometry. That means 4 coordination you can maximum have, usually speaking, right? So if you look at any of these intermediate, for example, you have 2 partners to attach together to form this product. So you have 2 coordination is taken by the 2 reagent you are using. And additionally, you have another ligand which helps you in carbon-hydrogen bond activation. That means that maximum coordination you are going to get is one coordination from the ligand. That is part of the reason why the ligand designing is so difficult in these cases, because all you need to do is to have a monodentate ligand, because more than monodentate ligand will kill your catalysis. You would not get any product often, because again, palladium is 2+, square planar geometry, 4 coordination that you have. 3 coordination is taken by the reagent or extra ligand which is required for CH activation. You need a monodentate ligand, but any of us who has done any chemistry, we know that monodentate ligand is not easy to deal with, because the metal will not be held by the ligand very tightly. So there is a degree of uncertainty where ligand is with the metal or metal is free in the solution. If metal is free in the solution, you are not going to get any selective chemistry that we are trying to discuss. And this is where particularly this sort of ligand designing becomes very critical, where it is a good sigma donor as well as pi acceptor, meaning that despite being monodentate, it can hold on to the metal very precisely. Again, being monodentate, still it can hold on to the metal center, making sure that metal is not going anywhere. It's localized, and the overall design and length ensures that metal is delivered only at that position, not any other position that is present in the organic molecule. Now, I'll come to that, the analogy with the enzyme. If you are thinking about the enzyme, metal enzyme particular, metal enzymes are capable of doing selective functionalization, right? That means only at one position it is doing the functionalization. I'll come back to that in a moment. What we are, I'm having, okay, maybe I should stand in here. So also, as I was trying to tell you, if you take this substrate, as you see in here, from this substrate, now we have a template, this one, huge template, this template. This substrate is wrapped up and bringing the heteroatom to the vicinity of this para-CH bond where metal is bound and metal is delivered perfectly at the para position. Once again, the similar analogy that you deliver where metal is required. We wanted to do, in these cases, the selective para-CH functionalization. The good thing is, if you are able to place the metal at a position of your choice, then you are not limited by the electronic and steric bias of the organic substrate that is present in your molecule, right? And therefore, irrespective of the electronic and steric bias, you can still get the type of reaction you want. Let's say a nitration reaction. You want at ortho position, meta position, para position, all can be delivered. Let's say an acylation reaction, alkylation reaction, carbon-carbon heteroatom, or any type of reaction you want to deliver at any desired position, that can be made feasible by placing the metal perfectly at a desired position, right? As you could imagine, there are a number of designing aspects in having this template. Well, one of the things is this is a huge transition state, and this CH bond need to be activated, not that one or not that one. That means the template overall design, the length has to be precise. If you miss a little bit, you are going to activate meta position or ortho position. Since it's a 18 to 20 member transition state, you need to have some sort of stability, and this pi stacking is given that stability. Since you need to make sure that the metal is coming over here, flexible rotation around the CC axis is critical. That means no substituent should be there at these positions. So the metal is really able to come over here. And more importantly, you need to bring your organic substrate and the template together, right? They have to come closer, and that means this Thorpe-Ingold effect imparted by this isopropyl group will be also critical. Essentially anything you change, even this heteroatom position from here to there, or this one here to there, well, you are essentially looking at product formation which is unselective or no product formation. So everything is perfected, again, then you can get the product selectively at the para position. This dimethoxy group also plays a critical role, specifically in the polar protic solvent, let's say hexafluoroisopropanol we use quite a lot. These cases, hydrogen bonding interaction between these two methoxy groups, make sure that this rigidity is obtained, and also this metal becomes more electrophilic in nature, so that CH bond activation becomes feasible. A lot of cases, particularly in the meta-CH functionalization in the last slide, we find that actually the meta-CH bond activation is no longer the rate limiting. You can even do the deuterium leveling. Well, for para-CH activation, still the CH activation step is rate limiting. We need to further develop this template, but nonetheless, this template works quite well for its selective functionalization. Well, one thing I'm trying to allude to, but never really mentioning, and that is these templates or the ligand, whatever you want to call it, or directing group, it need to be attached. If this is my organic substrate, I have to attach the template and then add the metal, and then we can do the chemistry. You can call it inorganic chemistry, you can call it organic chemistry, so be it, but you need to attach and detach. And that's not good, right? Synthetic chemist in this platform, we don't want to attach, detach all the time, because that will take 2 or total 3 steps. You have to attach the ligand, do the chemistry, and then detach it. The protection, deprotection type of chemistry that we usually see in the total synthesis. Well, that works when you do not have any option. That's the only option. I would say yes, there is no option for majority of the cases, and therefore this could be okay. But if you really want to make a difference, and if you want to see these methods applied in, let's say, in industry, you need to get away with the attachment, detachment. You need to make sure that one step, one good reaction happens. Right? And this is particularly where we started thinking, can we not have an attachable, detachable template, right? And particularly here, let's say if you are taking this aldehyde as a substrate, right? This aldehyde as a substrate, it can undergo an, in situ imine formation, attachable, detachable. So aldehyde is the substrate. You have at least 7 different types of carbon-hydrogen bond present in this benzene ring as well as this benzene ring. But if you take this benzene ring along with this aldehyde and this amine can form in situ imine, and then this nitrogen atom can come very close to this position selectively, and then the metallation can happen by the same mechanism as I was showing. Metal can be placed right over there. Once the metal is placed, you can then do organometallic chemistry to do various functionalization, such as different carbon-carbon and carbon heteroatom bond formation reactions. Well, you can do anything almost you want. Of course, it takes a lot of time. Part of the problem again is, although it is attachable, detachable, part of the problem is the template, this one, or the ligand, it need to be stoichiometric, because doing it reversible attachment and detachment under the reaction condition for an imine was not really feasible. Okay, so it is, although I would say this is what would be ideal, either you can take an aldehyde there and amine there, or an amine here, aldehyde over there, but this attachment, detachment can go up to a certain level and it fails. So to speak, the catalytic version of this reaction with respect to this ligand cannot be achieved. Of course, with respect to metal, it is catalytic, but with respect to ligand, it was not catalytic. More importantly, for almost all of our reaction and almost anybody who are working in this domain, specifically with the palladium catalysis, we usually need higher temperature, 90 to 130 degrees centigrade temperature, and also we need silver and copper salt, super stoichiometric amount. Now, if you are trying to do this chemistry in industrial scale, and if you need oxidant in super stoichiometric amount, you are going to create super stoichiometric amount of waste. And that means the waste disposal, waste management is going to be a huge challenge. For example, if you want to create 1 metric ton of product, you will have 3 metric ton of silver salt to deal with. This is not going to be, environmentally as well as industrially viable process. We wanted to do something about this oxidant as well as the temperature, 90 to 130 degrees C. We wanted to see if we can do this reaction at room temperature, if it is at all possible. Well, we'll try to work towards that, but let me then try to bring this analogy. This is a cytochrome P450. You can take pretty much any metalloenzyme, and you see this is the substrate. This is the enzyme substrate, this whole thing. and selectively this position is getting hydroxylated by this iron oxo species over here. Only this position, not these, none of these positions are getting activated. I would say the approach that you see is similar to what you see in here, not exactly copy pasting approach, but in a way, you take an organic substrate, many carbon-hydrogen bonds are present, and selectively only one carbon-hydrogen bond, just like over here, you are able to do the functionalization. Okay, I'll try to impress upon you a little bit more on that. So as I was trying to tell you previously, we were taking this organic substrate, let's say in black, right? You have seen something like this black organic substrate, and we were taking this brown color template. If we are taking the metal will be attached with this, and metal is delivered to this position, not at that position or in this position. Now, as I said, this is going to be attachment and detachment process. What we are recently able to do is just essentially cut it open. We take this as a substrate. It could be benzylamine, phenethylamine, fenpropylamine, and this NH, and just essentially cutting it open, this template or ligand we have taken, this ligand is interacting by anionic hydrogen bonding. Now it can be taken in catalytic amount. Previously it was really stoichiometric amount of things that we are doing. Now we can take it in catalytic amount, having an anionic hydrogen bonding over there. The substrate is over here, and essentially it can deliver the metal at one position and one position only, without touching any other position that is present into the organic molecule. Again, I would like to bring the analogy, although loosely, with this enzyme where you see the active site is there, how precisely enzyme was able to place the substrate in front of the enzyme or in front of the active site by virtue of having many weak interactions, be it hydrogen bonding, CH pi interaction, electrostatic interaction, hydrophobic interaction, name it, right? Enzyme did it perfectly for one substrate and one position only and one functionalization only. But in these approaches, the beauty, I would say, is essentially you can do these reactions for a variety of substrate, right? Enzyme, again, is really beautiful for one substrate, one position, turnover number unimaginable. For synthetic chemist, lesser mortal like any of us, we could imagine perhaps never to do such a level of high precision, but what we essentially can do is to have the strategy similar to what enzyme does, but for a variety of substrate. Again, we are looking for agromolecule preparation, pharma molecule preparation, where preparation of the molecule is important, efficiency is also important, but preparation of the molecule and in a site-selective manner is becoming much more exciting than anything else. And we can introduce both the metal as well as the ligand in catalytic fashion. And it is not limited to one type of reaction. You can, again, do a variety of reaction, which enzyme is usually trying to stay for one functionalization, right? Well, this is one of the approach. You might be thinking there must be other approach. Essentially, what we are trying to do is we are trying to take your organic substrate and trying to take the metal and try to place the organic substrate in one particular orientation so that despite having many different carbon-hydrogen bond, one carbon-hydrogen bond is getting activated, right? This is what we are trying to achieve. There must be many different ways how can you position the organic substrate in front of the catalyst. If this is your catalyst and this is your organic substrate, and if you want only this orientation, there must be many weak interactions you can work with. I have talked with you about the ligation between the metal catalyst and the substrate. That's not going to be good. The other approach, perhaps what we can work out, and this is where in collaboration with Bhaskar's group over here, Mayank, I learned that he's not here. Mayank was really instrumental along with Bhaskar to really nail down this system and understand the reaction mechanism. What we are trying to do is essentially try to put the substrate in absolute close proximity with the template by having a hydrogen bonding network. This sort of network you have seen in the form of, let's say, organocatalysis, right? You have seen the urea-based organocatalysis. So this urea-based organocatalyst motif with the substrate, and with the urea motif, we attach the template which will deliver the metal at a desired position. Once again, you can bring the analogy with the enzyme, where enzyme substrate is placed perfectly in front of the metal center by virtue of many weak interaction. In this case, only hydrogen bonding interaction was sufficient to place the metal with respect to the substrate precisely. Okay? But as you are hopefully noticing, what you are trying to merge is essentially organocatalysis with organometallic chemistry. This is organocatalysis, right? This sort of hydrogen bonding. But retaining this sort of hydrogen bonding for organometallic chemistry that is happening here, it is going to be tough, right? Because organometallic chemistry is usually very, very harsh, very strong reaction conditions are there. Under this strong reaction condition, attaching or kind of controlling and retaining this sort of hydrogen bonding is always going to be challenging. And this is where particularly we wanted to see if we can really develop some milder reaction condition where this sort of weak interaction can be tolerated and this organometallic chemistry can be done. Of course, another thing you are noticing, slowly we are building up towards the synthetic methodology or toolbox where various substrates, in the last slide I was discussing benzylamine, phenethylamine, penpropylamine, so on, can be selectively functionalized. In this case, you see, let's say nitrobenzene, and in over here, ketone, aldehyde, ester, amide, all can be selectively functionalized. If you are looking at the organic textbook, let's say 15 different types of substrate or functionalization you can essentially look at, right? So if we are able to incorporate this sort of functional moiety and can control the positional selectivity and the functionalization, and hopefully that will give us an opportunity to do a variety of reaction at a position of our choice. That will also give us the ability to modulate the reactivity at any given position to synthesize again the drug molecule, agromolecule, perfume, materials of our choice, that too at the extent or at the expense of the carbon-hydrogen bond. Of course, we did quite a lot of studies, in the want of time, I would not go into details, just to tell you that Bhaskar's group actually looked at the mechanism and inspired us to look at really hard in the experimental side as well to make sure that what we are computationally trying to understand and experimentally we are able to back it up. For example, what we learned that the carbon-hydrogen bond activation step is really not the rate limiting step. It's the beta migratory insertion and the subsequent functionalization becoming the most challenging or the rate determining step. Of course, the detailed study I'm not going to discuss. Bhaskar and Mayank will be able to tell you in detail. But in the interest of time, I'll quickly move on to tell you that we are mainly trying to focus on developing mild reaction condition. The goal essentially is to do the reaction at room temperature and not with those silver salt or silver copper combination, right? If you look at, again, the whole domain, we all are using 130 degree, 90 to 130 degree centigrade, and also super stoichiometric amount of oxidant. Now we started thinking, can we not do something differently? Okay. If you look at the catalytic cycle, roughly it looks like this, almost for variety of metal, variety of catalyst. Now you will have a metal catalyst, there is a carbon-hydrogen bond activation, metallation happens. This is the CH activation step. Usually these steps take very high temperature, like 90 to 130 degrees C, because usually this is the rate limiting step. It can vary, but this takes very high temperature. Subsequently, you have another substrate comes in, interacts, inserts. Overall, you generate a reduced metal species. So you started with palladium 2+, you end up getting palladium 0. But to complete the catalytic cycle, you have to go from palladium 0 to palladium 2, and this is where the stoichiometric amount or super stoichiometric amount of silver salt or silver copper combination was required. What we thought, can we not have a ligand palladium complex which can absorb light, and from a photoexcited intermediate or photoexcited state, we can do this CH activation. And therefore, let's say your barrier was from here to there. Previously, we were achieving by the thermal energy. Now, if you have a photoexcited state over here, all you need is this much of energy. And that can be done perhaps at room temperature. Indeed, that's what we are able to achieve. With a suitable ligand palladium complex, we can now do this reaction at room temperature. Additionally, very cheap photocatalysts like Yosin Y, Rose Bengal, and so on, we are able to show that this photocatalyst can be engaged constructively to have a photoexcited state by engaging the air or simple oxygen. We can take from palladium 0 to palladium 2. I think kind of in this case, we are able to demonstrate the limitation which has crept in over last 2-3 decades, that we need very high temperature. We need silver salt, copper salt, super stoichiometric amount. That can now, hopefully, not for all cases, but for a variety of reactions, it can be done away with, and then we are able to do these reactions quite efficiently. Well, I think the major beneficiary, another thing would be, see, let's say you do the asymmetric reaction. If you are doing the asymmetric reaction, you are trying to do the reaction at low temperature, like minus 80 degrees C. We are buying Julabos, Siskin, or other low temperature unit to make sure that the reaction is not done at high temperature, but at low temperature. Why? That is because we do not want the other enantiomer to be forming at all. We want only the low barrier enantiomer to be forming exclusively 100%. And the other one, which is really little bit high energy demanding, just little bit high energy demanding, we are ensuring that that's not forming by lowering the temperature as low we can go. Minus 80 degree, minus 90 degree, minus 100 degree, depending on the, the freezing point of your solvent and if your reaction is going at low temperature. Essentially, we are lowering the temperature to make sure that the other isomer, enantiomer in that case, for the asymmetric reactions, are not forming. But in these cases, we are actually getting benefit of regioselectivity. Previously, for example, if you are doing this reaction, which is a greener version of the Fujiwara-Moritani reaction, called the greener version of the Heck reaction, you take a benzene ring, let's say nitrobenzene, you try to do this sort of olefination or this sort of any of these reactions, you will have positional selectivity. Let's say mainly the reaction occurs in here, but some amount will be there, some amount will be there. In this case also, you will get some amount here and some amount there. Since we are now doing the reaction instead of 100 degrees C, we are doing at room temperature, what you see is exclusive product formation. Previously, it was, some of the cases, it was really bad mixture, I would say. And this sort of mixture, isolation, the running column chromatography of these is going to be very challenging because they are pretty much similar, having similar RF value. Isolation is a problem. Since we are doing this reaction at room temperature, also of course without oxidant, we really see that the temperature making a huge impact in the product formation that no other side product is forming, or the minor product formation essentially is cut down. So not only you get the greener version of the reaction, lower temperature without oxidant or harsh oxidant, you also have the benefit of producing one product and one product only. It was the major product, but minor product was notorious in terms of getting it isolated from the reaction mixture. You can get a much cleaner version of these sort of reactions. Okay, as I was saying, well, we are still trying to understand the reaction mechanism. Essentially, from the from starting point, you have a photoexcited intermediate intersystem crossing, 27.6 kcal per mole energy we are getting for free by the form of light. And this light energy is taking us from 0 to here, and from there we only need 17 kcal, which is achievable at room temperature. Roughly at room temperature, 22 kcal per mole is available. So the combination of photo as well as thermal energy is sufficient to do these reactions at a very high, at a room temperature. And the rest of the catalytic cycle I'm not going to discuss. It is similar to Heck reaction, or so to speak, the Fujiwara-Moritani type of reaction. Again, another exciting thing is if you are trying to really scale up these reactions, this becomes also useful. You can essentially scale these reactions up in multi-gram or hundreds of gram scale by taking the advantage of the flow chemistry, in-house flow chemistry setup that we built, or we have few setup from some of the commercial sources where we can do these reactions, such as this one. Essentially, to roughly speaking, we can put the ligand, catalyst, and the substrate together and shine light in here in this whole setup, and we can get the product formation pretty easily, making the way for scaling it up, hopefully for the industry if they are really looking for preparing this sort of molecule. Okay. Well, what I hope I'm able to tell you that at least for aromatic substrate, if you would like to see that functionalization or the product formation at a desired position, there is an opportunity to do this by attaching the ligand with your substrate. But that's not going to be a sustainable approach. We slowly, steadily try to move out of those attachable, detachable type of scenario. We are now having the catalyst separate and the substrate separate, just like what you would like to do the catalysis, right? Simple way, you take your organic substrate, you take your catalyst, take your reagent, everything, put together, you get one product at a desired position. And the way we are trying to do is taking the catalyst, substrate is kind of interacting with the ligand in a very weak manner, something similar to what you see in enzyme. The enzyme substrate is fixated in front of the catalyst by virtue of having many weak interactions. These weak interactions can be pi-pi interaction, CH-pi interaction, hydrogen bonding interaction, hydrophobic interaction, you name it. We are not able to put many interactions put together. Again, this is where the nature is more efficient and powerful than the synthetic chemists can ever perhaps will be able to do. But by doing only one or two weak interactions or incorporating these interactions, we are able to demonstrate that not only for one substrate, for a variety of these substrates, by keeping the catalyst controlled or catalyst same, we can promote a variety of reaction. Or at least that's what we want to go. Hopefully the decades of exploration will take you to a point where various substrates, many different substrates, we are able to do the functionalization in a site-selective manner so that we can do these not by functional group interconversion manner, but by through the cheapest possible source, that is the simple benzene, simple aliphatic substrate, and so on. So this is the overarching goal that we are working towards. Let me discuss a little bit on the aliphatic substrates. As you know, aliphatic substrates are going to be a little bit more challenging than the aromatic substrates, right? Aromatic substrates are having the pi cloud, aliphatic substrate doesn't, right? Well, I'll not get into way too much of details what all we have tried to do so far, but I'll come back to let's say some of the molecule which will look like natural product. These are actually natural product. There is a class of natural product or several classes, subclasses of natural product which are, let's say, bicyclic lactone. Right? These are great molecules. As I have tried to highlight over here, if you would like to synthesize any of these bicyclic lactone, one of the way to synthesize them would be to essentially open it up, right? Just for simplicity, let's say you would like to have this molecule. If you open it up and if you can form a carbon-oxygen bond between this center and that center, you will get your natural product. But the problem here simply is, of course, this can act as a ligand for metal. Metal can be bound over here, and you could expect this position is getting activated. But the issue here again is, this is the alpha position, this is the beta position, this is the gamma position. Again, this is the alpha position, this is beta position, and this is also the gamma position. Now it's going to be the competition between this methyl and methylene. Both of them are gamma. And if the metal has a choice, which always metal has a choice, it will end up activating always here, but never there. Because the metal alkyl, this is going to be primary in nature, this is going to be secondary in nature. This is less sterically demanding, this is more sterically demanding. That's what we tried to push over here. So if you are trying to take the metal, metallation will happen selectively at this position. You would never get the metallation over there. If you do not get the metallation over there, cyclization over here will not be possible. If cyclization over here is not happening, those natural products are not going to be formed, right? But we saw that there is an opportunity. Of course, this can lead to a very good intermediate and subsequent product, and that is going to be this bicyclic lactone. So, these pyrocycles. This is also natural product. There are many targets, but this is also we are able to achieve because this methyl activation is happening in here. Now, that's not definitely going to take us to those bicyclic lactone type of natural product that I was showing. This is a good reaction. What we noticed when we were trying to work on this, that this step is really disfavored. This is same for, let's say, any of you who has done Buchwald-Hartwig type of coupling. If you do the carbon-nitrogen bond formation, reductive elimination is never the rate determining step. But for carbon-oxygen bond formation, reductive elimination is the rate determining step. That's the most difficult step. So what we having here is this as a rate determining or disfavored step. If there is an opportunity that this intermediate is not really forced over here, or the reaction condition is not very harsh, essentially this step is not going to happen. And under that condition, what will have an opportunity to have the metal actually at this position. So because this intermediate is difficult to form the product, this intermediate can then come over for the other intermediate possible. And of course, the carbon-oxygen bond formation from here is also going to be challenging. But in this case, this is a gifted case, we have a beta hydrogen over here. Here there is no beta hydrogen, alpha position, beta position, there is no beta hydrogen. But in this case, you have alpha position, beta position, there is beta hydrogen. If you have a suitable ligand, you have an opportunity to do the beta hydride elimination. And therefore, you can roll over and do the cyclopladation or oxapladation type of intermediate to form this sort of bicyclic lactone. I'll take it slow and tell you again. So there are two opportunities, as you can see. The opportunities are either this one, the metallation can happen over there or over there. It is exclusively always this one. But the product formation is difficult, right? Under this condition, where more preferred intermediate is not going for the product formation, there is something called Cartan-Hammett type of principle or Cartan-Hammett situation. Under this condition, preferred intermediate can equilibrate to a non-preferred intermediate. Of course, this is not preferred, but the subsequent step is really forced by a bulky ligand because there is a beta hydride elimination. Here, similar intermediate is not possible. And therefore, this ligand can essentially force it through to the product formation. Okay? So this is again called classical Cartan-Hammett type of situation, where essentially the red dot is where you start from. This is the low energy barrier, if you are seeing. This is the low energy barrier pathway. The intermediate forms here, but the product formation is difficult. Under this condition, after forming over here, it can equilibrate back to this intermediate. Although this intermediate is little bit difficult to achieve, but the product formation from here is little bit easier. You see the cartoon? So it goes up to here, but the product cannot be formed. It goes back, and then it can form the product exclusively on the other side. Again, this is what is the classical Cartan-Hammett type of situation. So don't believe what you see. If you isolate an intermediate, not necessarily that is going to be the right intermediate leading to the product. It could be just intermediate, easy to form, and you are able to crystallize. That intermediate can interconvert to some other intermediate, give you absolutely different type of product. So your intermediate sometime, this is not happening all the time. Most of the time, all of us are correct that intermediate isolation will lead to the product formation. But cases can be also made in some instances like this one, where the more preferred intermediate is not going to go for the product, but that intermediate can equilibrate back to another intermediate which is not preferred to start with, but the product formation is preferred, as you see in there. Once you are able to do that, essentially, you can then do this sort of reaction quite exclusively and quickly. Okay, how much time I do have? I'm going very slow here today. 6 o'clock, okay, all right. How much time I have? 5 minutes? Okay, I'll be very quick. So, this essentially leads to, let's say, 7-10 different natural products, formal or total synthesis. You can do many of those. In 2 minutes, I'll be very quick. I'll try to tell you that some of the time, what we try to do is we are not able to do this reaction in an asymmetric fashion by CH activation, by using the normal catalyst. Under those conditions, what we try to do, we are trying to see, can we not do the catalysis, instead of doing homogeneous catalysis or heterogeneous catalysis in our flask, can we not put those catalysts inside the enzyme and try to utilize the enzyme architecture for inducing the stereochemistry, because we are not always good at inducing the stereochemistry by doing the normal flask homogeneous or heterogeneous way. This is something called artificial metalloenzyme. If you are familiar, few names come into picture very quickly, let's say Francis Arnold group and Tom Watts group and so on. I will keep it very short. We didn't want to do these catalysis in the metalloenzyme, but in a protein which has no metal, and we wanted to bring our metal inside. By bringing the metal inside, we are trying to utilize the cavity of it to induce the stereochemistry that is happening over here. Because this is chiral, this chiral pocket, unlike the ligand, this chiral pocket will induce the stereochemistry in the product formation. As I said, I will keep it short. What we are able to show that in the biotin, if you are attaching this metal center, inside this cavity, which is chiral in nature, and if we are changing few amino acid residues, this is a crystal structure of the protein that we obtained, it shows that these 3 residues should be modified, and if we modify it, we get very high levels of enantioselectivity for this product. Again, this sort of product formation you have seen, let's say from Amit's group, very beautiful work, but what we are able to do is this sort of reaction inside the enzyme pocket, and now we are able to do acceptable levels of yield and enantioselectivity. More importantly, so in this case, I said that we will get the R-selective product by having this CP star ring on the tyrosine. That's the modification we have made. But the moment we have modified the other way, where phenylalanine is there, this pi stacking is set. Previously, pi stacking was between these 2 units. By changing this amino acid residue and flipping the metal from the top to bottom, as you see in here, now we get the S-selective product. Okay? So again, by utilizing the chirality of the protein, doing the reaction inside the cavity of the protein, we are now able to tune the stereoselectivity that we would like to achieve in these cases. Of course, it's this sort of exploration takes quite a long time, but overall having the right crystal structure and understanding, it can help. Well, I'll take maybe another 5 minutes because I think I should have started with this story, and that may not be, way too exciting to start with. If you are thinking about it, this is about the holy grail of organometallic chemistry called carbon-carbon or carbon-heteroatom bond formation, namely the cross-coupling reaction. See, part of the reason cross-coupling or the organometallic chemistry came into the existence as well as the popularity of it is due to the cross-coupling reaction. Let's say, one of it is definitely cross-coupling reaction. Other could be, let's say, your metathesis reaction, you name it. Many organometallic chemistry is there. But cross-coupling reaction, of course, is one of those favored reactions which everybody knows, right? Let's say Suzuki coupling. I think everybody in this room has heard about the Suzuki coupling, right? It's a great reaction. Everything is given to it. Everything that a dream reaction can achieve, it has achieved. But at the same time, it has many, many limitations. Limitations simply are, if you are trying to do these reactions with heterocycle, well, you are not going to be happy. You are not going to get your product. Particularly 5-member heterocycle with multiple heteroatom, the type of molecule that we take as medicine, Many medicine cannot be prepared by Suzuki coupling or any other cross-coupling reaction because the type of substituent it has, the type of heteroatom it has, it's not going to allow you to do the cross-coupling reaction. And more importantly, let's say Suzuki reaction, you have boronic acid. Boronic acid stability is huge issue. It usually proto-deboronate. You try a boronic acid, you essentially get a benzene ring or heteroaromatics and the boronic acid part separate. They are not together. They hydrolyze. Proto-deborylation happens. Another most important point is these boronic acids are usually always synthesized from aryl halide. So you take bromobenzene, you convert it into the boronic acid. So before making this cross coupling, you are preparing the starting material by many different steps. That is definitely we are not thinking about. We are trying, academically we are just buying boronic acid, but industrially you have to prepare boronic acid, right? What could be perhaps better way to do this reaction is if you can couple between the aryl halide and aryl halide. Let's say aryl bromide and aryl chloride coupling, aryl bromide and aryl iodide coupling instead of aryl bromide and boronic acid. Boronic acid has to be prepared and it is very little available. Halide halides are available in large quantity. And therefore, you can do these reactions quite efficiently. Essentially, that's what we are able to do. The challenge here was, if you are trying to do aryl halide and aryl halide coupling, and you want to couple them, the problem is it will give you homocoupling, as well as proto-dehalogenation and proto-dehalogenation. That's you see. So you have multiple product formation. Instead of one product that you are looking for, you have these sort of other 4 product formation, and there was absolutely no way to solve it. I'll be very quick. What we are able to show that now, by taking 2 halide put together, you can get this product exclusively without forming those other 4 side products. I believe we have stumbled upon a completely new way of doing organometallic chemistry, that to the light, and that is we are now able to have a 2 catalytic cycle. In the first catalytic cycle, we have a photoexcited intermediate with a suitable ligand, and this aryl halide, which is more reactive between the 2, this is the more reactive, will give you a palladium, let's say metal, metal 1 as well as radical. You need to make sure that this has stability. If you have enough stability, it is not undergoing homocoupling or proto-dehalogenation. In the meantime, the one which is not reactive enough in the photo condition, that can undergo the traditional oxidative addition. And that's what has happened. And these 2 intermediate, if you are able to couple, and if they are not undergoing proto-dehalogenation or homocoupling reaction, then you have an opportunity to have an unique intermediate, which is palladium 3, to give you the heterocoupling which you are looking for. Essentially, what we are trying to tell you is, all those cross-coupling reactions are great. I don't think we are trying to compete at all. Cross-coupling requires an electrophile and a nucleophile, aryl bromide and a boronic acid, aryl bromide and a zinc reagent, aryl bromide and let's say organolithium reagent. All these reagent you need to prepare from aryl halide. Now we are able to show that 2 aryl halide, essentially 2 electrophile, no nucleophile is involved. By tweaking the reaction mechanism, as you see, a radical plus a traditional mechanism combining, we are now able to do these reactions in a very low temperature, such as room temperature in this way, and we can do these reactions. Of course, I will be very quick, just a few seconds, that it requires the ligand, the development of the ligand. You need to develop the ligand, and that's the only way to do it. A suitable ligand which supports both the catalytic cycle. There is 2 catalytic cycle, double the problem, double everything. So you have to make sure the ligand is good, and we have stumbled upon or designed, I would say, this ligand which we are calling as Sudip-Phos. So essentially this dimethyl amino group is extra compared to the known ligand, and this essentially makes sure that it gives only one product or sometimes very little other side product. By doing so, what we are able to show that some of the heterocycle, some of the coupling which were not happening earlier, some of the very challenging heterocycle which perhaps will never happen in Suzuki coupling type of reaction, it can be incorporated not only with the 2 halide, you can take the triplet and aryl bromide as well. But I guess the most exciting part is we are seeing bioorthogonality, meaning that we can take the peptide and try to couple them as well, right? Perhaps one day, hopefully, we'll be able to take the DNA as well as couple in DNA as well. And as you could imagine that these reactions also are scalable. Okay, we started demonstrating that this simple experimentation of the halide is going to be scalable, and I think this is something finally we are getting into where perhaps the industry will be really, really excited to see, because industry kind of cannot live without the cross-coupling reaction at this point. Of course, all other reactions are great, but the cross-coupling reaction is going to give you the product in industry. If you are making 10,000 compounds for your, let's say, drug delivery program, you need to use cross-coupling. And there are many limitations of the cross-coupling. If some of those limitations can be overcome by using even the easiest possible starting material, that's going to be really, really wonderful. Well, we are, again, very, very happy. I am particularly to be here. Thank you so much for your kind hospitality. Thank you so much for your kind attention and having me here. It's been an absolute pleasure to be here. I really loved my journey over here, and all the interaction throughout I do have. And thanks all the funding agency and all my collaborators. Of course, Bhaskar, it has been a pleasure to work with you. I'm sure we'll go hopefully decades in forward to work together to develop an understanding of some of the reactions that we are trying to develop, and all my other collaborators as well, and all my students. And no matter what I say over here, everything, literally everything, from the planning stage to the execution to the manuscript communication, and everything has been done by the student. And I am not stretching at all about their contribution. They're the one who are the backbone of anything that we do in our laboratory. With that, let me thank you once again for your kind attention. I'll be very happy to have your question if time permits. Thank you very much.
Thank you, Professor Maiti, for such a wonderful talk with exciting science. Okay, now the floor is open for questions. Yes, there is something at the back.
Thank you so much, sir, for your wonderful talk. Sir, I am Adarsh from PhD Chemistry. Sir, I have few questions.
Sure.
Sir, first thing, in one of your NPTEL lectures from metal-mediated synthesis that was uploaded in 2018, Exceed, sir, you told that palladium-0 is the more reactive species that we require in our reaction. But all the commercially available catalysts are either in palladium-2 or palladium-3.
Right.
You also emphasizes on why we purchase palladium-2 due to stability over the redox potential of that PD0 that can be interconvertible. So, sir, can we have any relative ligand that can stabilize PD0 in essence of PD2 for those reactions?
Yeah, that's an important question. This is a fundamental question, I would say. Yeah, if, as you know, PD2-DBA3, PD-DBA2, the problem here is, these ligands which are stabilizing palladium-0 and commercially making it available, like DBA, dibenzyl acetone, these are also a good ligand, right? They are good ligand, and that's why they are stabilizing palladium-0. But these good ligands, like DBA, they cannot do essentially any cross-coupling reaction. You need a phosphine reagent, for example, or other ligand to make the palladium-0 chemistry alive. So under that condition, when you know that your ligand, let's say phosphine or other many ligands that is there, this is going to be so expensive, and if those DBA has to really compete with the phosphine, you are not going to get a great reaction. Let me rephrase. In order to stabilize palladium-0, you end up adding DBA. This is what the commercial availability of PD, DBA2, PD2, DBA3, or many other these sort of bidentate ligand. Nowadays, quite a few others group has been working and trying to bring the ligand palladium 0 complex. Now, this ligand and palladium 0 complex, they are able to stabilize palladium 0, but this is an extra luggage. This is an extra luggage, particularly because these ligands itself, like DBA and others that are known, they cannot do the real chemistry, let's say cross-coupling chemistry. They are not good at cross-coupling chemistry. Then what happens when you are adding your cross-coupling ligand, the very expensive ligand, then that ligand has to compete with this DBA or other ligand. Then you are having a ligand exchange competition. Ideally speaking, you should not have competition of your expensive ligand with cheap ligands such as DBA, right? This is where it is preferred that you start from palladium 2, like palladium acetate, you in situ reduce it, acetate is going out as acetic acid, so you do not have any competition with acetic acid versus your phosphine ligand, and therefore, let's say phosphine ligand can sit on the metal very easily. There is no competition between acetate or acetic acid and your phosphine ligand, right? And this is precisely the reason we do not want, or anybody actually I would say doesn't want to see any ligand with the palladium 0, and that's why purchasing palladium 0 may not be the best idea. Okay? So purchasing palladium 0 comes with those extra luggage of that stabilizing ligand. Getting rid of that stabilizing ligand from the catalytic cycle is very tedious, and you have a less than perfect reaction with your main ligand, and therefore you are happy in reducing palladium chloride to palladium 0 or palladium acetate to palladium 0 and then going on with the chemistry. Okay? There are many ligands nowadays available for stabilizing palladium 0. It works to certain extent. I don't want to discredit anything, but that competition is always there, which is very difficult to overcome. Yeah.
So my second question is from sir, that artificial metalloenzyme.
Yeah.
So where you used biotin. So we know that biotin is a bicyclic structure with a urea type of motif as well as a sulfur atom, whereas side chain is carboxylic acid. So sir, you are giving 3 to 4 extra heteroatoms in your spacer, not in the enzyme. That is actually the streptavidin or anything else that can perfectly bind with biotin.
Yeah.
So if we are introducing that much number of heteroatoms like O and S, is there will be any competition for the rhodium or ruthenium to be directly selected in that carboxylic acid or any ligand attached to it?
Right, you are right, absolutely correct. Part of the thing is the denticity. If you look at any of the heteroatom that is there, this is going to make a huge metallocycle, right? All those heteroatoms over here, if it is going to the metal, this is going to be a huge metallocycle. In any way, this is like kind of a rigid, I would say, this part is rigid. And since the metal is over here, metal sees anything that is nearby. I got your point that there are many other heteroatoms that can influence the process with the metal or compete with the metal. But the thing here is, the metal is really in a site isolated manner. In this site, it is fixed, and therefore it is seeing only these sort of heteroatom. Okay? So you are creating a micro environment or pseudo environment for the metal so that other things are less preferred. You are absolutely correct, things can go wrong. Any mutation that we are trying to do, it can destroy the whole protein, it can denature the protein, it can have many other bad effects. But despite having all those possibilities, we are in the successful cases, there are many unsuccessful attempts which we do not understand what is happening, but at least for the successful cases, those sort of unfavored or preferred binding is not happening with the other heteroatom that is present in the close vicinity. It's the amino acid residues which are dictating the term by virtue of having the metal center in the close proximity. And again, I appreciate the question. This is very critical, and we try to deal with it by making sure that all those things are not happening. Okay? There is no other way to deal with it. And in a lot of cases, the macrocyclic formation is so very unpreferred. Perhaps these amino acid residues still can have their way to ensure that the real catalytic cycle is going on. Yeah.
So my last question.
Sure.
So luckily there are many safer alternatives of chemicals or carbon or fossil fuels like electricity. So you have not given any emphasized on electrochemical CH activation or anything related to that?
I'm sorry, in the interest of time, I did not do that, but I can just show you in a moment if I'm able to see it. No, not this. Okay. We do quite a lot of these electrocatalysis. For example, over here, this is a work with Bristol-Myers Squibb. What we were able to show that we can instead of having the the oxidation or the chemistry controlled by the photocatalyst, we can do this reaction by electrocatalysis as well. But the mechanism actually is a little bit different than the photocatalysis or thermal catalysis. It happens a little bit differently. Not only that, we can do these reactions even in an asymmetric manner. So these are unpublished results, and we can do a lot of the electrochemistry, which we are presently doing. A lot of those will be coming hopefully in next few years or so. Yeah. Thanks.
Thank you so much, sir. Thank you.
Thank you.
Good evening, sir. First of all, thank you for the wonderful talk. My question is, in the part of aryl halide cross-coupling reaction, you have showed that there are very limited option in boronic acid or zinc or some, magnesium, BF3, all these organometallic partners. The precursors are very limited. But can we try, or have you already tried the organometallic partners to perform this type of reaction, or just you have only focused on this aryl halide part?
Well, again, the world has exploded since 1970s, 80s to do the cross-coupling reactions with every electrophile and every nucleophile possible, right? The world doesn't need me at least to do yet again those reactions, okay? Because again...
No, sir, I am asking that 2 boronic acid or 2 like this, only 2 organometallic partners.
Oh, okay. The nucleophile coupling, you are saying, instead of electrophile-nucleophile coupling. We did not look at those so far, partly because then the problem, I would not say problem, the thing is you need to kind of oxidize the nucleophile to bring it into a, let's say, radical stage and then do it. One can certainly think of doing that. That's again a great thought. We are doing the electrophile. If somebody wants to do a nucleophile coupling, yes, it's a thought. But part of the problem, what I'm trying to impress upon you, is this nucleophile has to be prepared from electrophile. Like aryl bromide to aryl zinc reagent. This is the Grignard preparation. You start with bromobenzene, you add magnesium, you get ArMgBr. Like Grignard reagent preparation. It's the preparation of the nucleophile is problematic. Because you see, 50% of us will fail in preparing the Grignard reagent, right? It's a challenging. There are a lot of challenges. People are trying to solve this problem by having, let's say, turbo Grignard. So to call Paul Nochel's chemistry and others. There is a whole lot of chemistries going on to prepare the nucleophile from the electrophile. Electrophile is readily available, but nucleophile is very difficult to achieve, and the preparation and the stability of these are highly questionable. Now, this is part of the reason why we didn't try to go for nucleophile coupling, but I would agree that scientifically it's a good proposition to do, but we didn't try. We tried to do more of, let's say, practical aspect of the cross-coupling reaction, where we try to do an electrophile coupling. So the aryl bromide, aryl iodide, aryl bromide, aryl triplet, aryl bromide, aryl chloride type of coupling, so that you have that readily available starting material, and you are not struggling to prepare the starting material. Again, in industry, one of the major thing is how easily you can prepare thing and how scalable your method can be, right? Because sometimes we need thousands compound, sometimes we need one compound in metric ton scale. So those, I would say, in doing that in nucleophile coupling manner will be a little bit or a lot more challenging, okay? So it's again, scientifically it's a good thought, one can do. I would say taking the nucleophile and oxidizing is the way to go perhaps. If you are interested, absolutely, please go ahead for it. Yeah.
Thank you,
Thanks.
sir.
Any other question? Yeah, there is.
Thank you, sir, for delivering this nice talk.
Oh, hi.
So lastly, you tried to mention this electro-oxidative process for asymmetric organic synthesis, right?
Right.
So particularly maintaining the chirality of the product. So is commercially these chiral electrodes are available, or how you are controlling the stereochemistry?
Right. The stereochemistry is induced by the ligand for the metal center. Okay. I didn't present it today. I was just, kind of briefly showing. We have a chiral ligand, okay, for the metal center. A lot of these cases are the monoprotected amino acid as the ligand. So the chirality of the amino acid chirality we are trying to transfer on the product. Okay. So the ligand metal complex itself is chiral. And then we are trying to get into the axial chirality in that particular case that I was trying to show you, right?
Okay, sir, I have one last question. In continuous and the batch flow electrosynthesis process, scalability is one of the bottleneck problem.
Right.
So how you are controlling your reaction? I mean, gram scale
for the
synthesis.
electrochemistry, of course, we didn't do it yet for the electrochemistry scale up, but one can, we are also having a collaboration with an Indian industry where we are trying to essentially have a bigger platform for the electrochemistry. We have, I should have demonstrated, so that Electrasyn, one of the company, I don't have, it's one of my collaborators company. We are trying to collaborate with them, and we are together trying to develop this Electrasyn, which is going to be a much cheaper version of, let's say, ICA, which are very expensive. And we are trying to have a bigger setup. Essentially, you do the reaction in a bigger setup. It is possible. It has its challenges, but it is possible to do. Electrochemistry setup, just like the photochemistry setup, as I was showing by the flow chemistry, we can really scale it up. It is also possible to do either the batch process or the flow process. We didn't get into there yet, but it is possible to do the scale up by utilizing the electrochemistry. But it's not necessarily always going to be really easy to scale up all the time, but it is possible, certainly.
Thank you, sir.
Thank you.
Is there any question? Oh, okay. I think students, you are done? Okay.
So, Professor Maiti,
Hi,
great talk as usual. So, I have one question from that photochemistry work. So, the regio selectivity in that work for electron deficient arenes, it was meta-selective, and for electron rich arenes, it was para-selective. Yeah. So, how exactly this regio selectivity is determined?
Yeah, essentially one of the parameters is there called Fukui indices, which, let's say, Bhaskar can calculate for me. The most nucleophilic position, because the olefin in this case is an electrophile, if I have the little bit higher Fukui indices value, that means that position is more nucleophilic. That is the position that's going to work. So we have kind of seen it again and again and again. Some of the Fukui indices value are available in the literature. Some of them can be calculated in collaboration or little bit skills that we have inside the lab. We can calculate the Fukui indices. That means, let's say, if you are looking at this one, the ortho position, let's say, I forgot the values. I would say this is the one which is most nucleophilic, similar to here and similar to here. This is nucleophilic, this is little less nucleophilic, this is also nucleophilic. It's the challenge between this position and that position. And this position, mostly due to the steric region, it is winning. But sometimes it can be complicated as well, right?
But the rate limiting step in this case, or the photo active, or like the where the photo excitation actually comes into play, is the CH activation, right?
This is no longer the rate limiting step. CH activation, as again in the calculation what Bhaskar has done for us with the urea-based motif, CH activation is no longer the rate limiting step. It's the beta migratory insertion. The insertion, the carbon-carbon bond formation is the stereo and regio determining step for the asymmetric catalysis as well as the other normal catalysis. Not necessarily always CH activation has to be rate limiting. More often that is rate limiting, but the moment your catalyst is becoming really good, for example, that the one I was showing in here as well, for most of our meta-CH functionalization with specifically the pyrimidine-based ligand, this step is no longer the rate limiting. It's either this one or that one is the rate limiting. If the ligand is good, CH activation is as good as any other step. Okay. If your chemistry is strong, this part is not really rate limiting. It's the bottom half becoming the rate limiting part. This is what is similar to, as I was trying to tell you, let's say Buchwald-Hartwig coupling, if you are trying to do with amine, it is the deprotonation is the rate limiting, deprotonation of the amine. But with alcohol, let's say phenol, because the OH acidity is very high and so on, so deprotonation is not the rate limiting, it's the reductive elimination, the product formation step is rate limiting. So of course this is not going to be universal, it's going to depend on the substrate combination as well, what type of substrate you are trying to put together, but it's the subtle interplay between the steps, which one is rate limiting, it's varies. As I said, for carbon-nitrogen bond formation in Buchwald-Hartwig, it's the deprotonation is the rate limiting, but for carbon-oxygen bond formation, it's the reductive elimination is the rate determining. Similarly, for some of these cases, depending on the ligand we have and the reaction condition we have, mainly the ligand I would say, that is going to determine whether CH activation is rate limiting. Initially, let's say 5 years back, 10 years back, people would like to believe always it's going to be the CH activation which has to be rate limiting because it is CH activation. Well, since the development has gone to a point, this is made so easy, the ligands are now more suitable. Previously what has happened a decade ago, the ligands were not good for the metal. Somehow we were able to do the chemistry, but the ligands were not good. Now the ligand development has come to a point where that step is taken out of the equation in the larger scheme of things. Other step becomes more problematic. So you need to now solve the other step, and that's how the whole catalytic cycle can be very efficient. The way, let's say, enzyme works, everything is so facile and there is no side product formation, there is no off-cycle intermediate, so to speak, there is no catalyst poisoning. Everything is happening very quickly, but for almost all the metal catalysis or any synthetic catalysis, at least one of the steps becomes so difficult that you tend to go to catalyst deactivation or poisoning or off-cycle intermediate, and then your catalyst is dead. So this is a constant struggle. You overcome one step, then another step becomes difficult, but the best catalysis will be everything is perfect or as perfect as possible. Of course, still there will be a rate limiting step, but that rate limiting is not going to be too much limiting what is happening in enzyme. Everything is perfect, everything is good. So this is the ultimate goal for catalysis. So make sure that everything is great, right? Okay. Thanks.
Yeah, thank you. Then like now my second question is like in this photochemistry work, your CH activation is made easier due to the photo excitation. Right, and that's why you could bring the temperature to room temperature.
Right.
Now, for your other CH activation reactions where you used far more complex ligand, for example, that hydrogen bonding interaction with the organocatalysis type hydrogen bonding interaction.
Okay.
Just have you thought about, so this reaction you had to do in at what temperature? What temperature was needed?
This one, I believe, again, the temperature is fluctuating from different slide. Yeah. I believe it was 80 to 90 degrees centigrade. Okay.
So I was thinking, so since this is also a complex ligand and definitely a photochromatic compound, will it be possible to do this particular CH activation, site selective activation, at lower temperature with that? Like, this is a very trivial way of thinking, but have you thought
it's
about that?
absolutely right. I mean, I would like to say this is what the goal. We tried, we failed.
Okay.
This is again, you try to sell apple, you get an orange, right? You get an orange, you try to say it is lemon. So always there is the ground under the feet is always shifting. I wish it was. I thought it would be. But something, because the thing is, the moment you are trying to bring too many things together, a lot of things may be also broken. What happens, how the light is, destabilizing this, we don't know. And also another problem we are seeing, well, let's say that only at this point, since this is absolutely, I would say, very recent, we don't understand it in a way that why in this case light didn't work. Okay, but the target, absolute target, is to make sure that it works under light also. It works with electrochemistry also. We didn't try it yet, but then you are becoming, or you are having a reaction condition which is mild or milder, and therefore a lot more can be done than those which we are doing before. Yeah, hopefully one day.
Okay.
Thanks.
Just one final question.
Sure.
And this is more like a theoretical and hypothetical question. So the Curtin-Hammett diagram that you showed, that graphic. So of course the favorable intermediate could not proceed further because the next step is energy demanding, right? So the initial approach of CH activation that you showed, like the meta-selective or para-selective, so the length of the spacer was fixed. So the length of the spacer was big. So now in a theoretical way, if we think about that, if you choose a spacer, if you choose a ligand, geometrically it is supposed to do meta-CH activation. But after the CH activation, the culmination step is not favorable. And therefore, it goes to a para-CH activated intermediate, which is less favorable. But anyway, it goes there and leads to para-CH activation.
Absolutely. I mean, I do have an example, not in slide. Yeah. Yes, we are able to see that. Now we are able to see that with a meta-directing group, we can push it for the para as well. Yeah, absolutely. Because the difference, energy difference, again, if you look at the computational, if Bhaskar is calculating, it will be very little between the meta para. There is a distinction between the two, but the difference is not high enough that always you would be able to really discriminate very effectively. So yes, to answer your question, it is possible, but not in every cases, but in select few cases, we are able to show that with the meta-directing group, we are actually getting exclusively para. Yes, this can be traced back to the same Curtin-Hammett principle, but again, as I said, Curtin-Hammett is not going to set in all the time. It is a special one, and only in special circumstances it can be applicable, and yeah, I'm really happy that it is working. It will take some time, but hopefully one day soon, yeah.
Thank you very much. Thank you.
Yeah, thank you, Debu. Nice presentation as usual. So I have one question regarding your photochemistry. Right. So you are saying that you have excited the palladium acetate and the reaction could be done at room temperature instead of high temperature. Right. So is there any direct evidence that the catalyst is really excited and temperature is lowered because of that particular chemistry? Because like it's very hard, like palladium acetate, it doesn't have any such ligands which can like absorb the light and go to the excited state.
Okay, of course, direct evidence is very difficult to give. Thank you, Amit. So what we have is the, let's say, UV visible spectra. If you record a bunch of ligand metal complexes, you prepared it, and you are able to see indeed there is a strong band in the visible range where we are really exciting. I do not have absolute critical evidence that this is the one what is happening, but there is UV visible band with these ligand palladium complexes, which is again giving some sort of evidence that this is happening. And we are indeed now trying to measure these, in collaboration with some of my colleague, let's say Professor Aninda Datta's group, we are trying to see the excited state The lifetime and the decay profile, it's going to take a little bit longer, but overall we believe that that's what is happening. The experimental evidence at this point I do not have very conclusive, but I believe that that's what is happening. Okay, and also there are number of experiments one can do by varying the light intensity, how it propagates, if you do it double, triple, there is a pattern to find in the physical organic chemistry. So those sort of experiment we are doing. Also in select few cases one can do the Stern-Volmer quenching type of thing. Again, that's not really correlating directly with your question, but some of these experimentation are underway. So that we can be a little bit more confident than what we are right now. Yeah, thanks.
Yeah. And last question, when you did this transient directing group strategy, your amine is aromatic amine.
Right.
So the imine formation might not be reversible because of that. So did you try any reaction with the aliphatic amine?
Yeah, part of the problem was this template with aliphatic amine is not that great. Okay. This reaction, the efficiency was not that great. So we were kind of ambushed to use the aromatic amine. We were forced, essentially forced. But now we are trying to, so let's say benzyl amine, we are now trying to put the benzylic position substituent to put the Thorpe-Ingold effect in so that it becomes better. So those developments are ongoing. It will just take a little bit longer.
So that like it will be a true transient.
True transient intermediate, yeah.
Thank you, Debu.
Thank you. That's really exciting questions, yeah. Thanks.
Okay. Yeah, hello.
Sure.
That's a great talk. So enjoyed a lot. So
thank you.
yeah. So I have one just a curiosity. It's not a question. So it's the cycle of the two cycle, the photocatalysis and the cross coupling. So I can see that if you excite the palladium, it can only reduce aryl iodide.
Yeah.
Right? So that means the reduction potential of this palladium complex in the excited state is such that it can only reduce aryl iodide, not the bromide. And that's why the selectivity is coming, that you can do the heteroaryl coupling. Is it the right thing?
In a way, yes. It's a very important question. We are still trying to address it. In a way, yes, that's what we would like to believe. But it is not going to be really always the case, because the moment you have substituent, you are changing the reduction potential as well, right? This is maybe true to start with, let's say, between a bromobenzene and an iodobenzene. Now, what happens when the bromo is substituted, it can get complicated, right? If it is an electron withdrawing substitution versus an electron rich substitution, you will be having the other way around. So what we believe is that, again, the proof is yet to come, difficult to prove at this point. We have some evidence, I can talk later on as well. So we believe that the one, irrespective of iodide or bromide, the one which is having the lower barrier, that's what is going to do for the radical type of intermediate. It's not necessarily, for the simplicity I put the iodide, it's not necessarily has to be the iodide. If a bromide is even more easier to do than the iodide, it can go. See, what we are believing is from the ground state, there is a photoexcited intermediate. From the photoexcited intermediate, there could be a traditional oxidative addition as well as a radical intermediate. Now, these two intermediate, the oxidative addition and the radical intermediate, can be in equilibrium. This equilibrium is rapid. Okay, so the barrier for these formations are maybe similar. Again, we are trying to gain the evidences for that. Barrier for oxidative addition from the photoexcited intermediate versus the radical intermediate may not be differing too much, but it's the interconversion between the oxidative addition and the radical intermediate that is actually setting the step what is going on in the next, right? So if the barrier is high, then definitely only one of the intermediate, let's say the radical intermediate, will go on. When the barrier is very little, then we essentially don't know which intermediate is reacting, right? Fortunately for us, I think the ligand is setting up the barrier in a way so that still, despite having very little differences, we still have a leeway to influence the process. Okay, it sounds a little bit complicated because part of the thing is it's two catalytic cycle. People are usually dealing with one catalytic cycle, one traditional catalytic cycle. Actually, that's why what we are trying to see is now we are taking one ligand for this catalytic cycle,
Yes.
and another ligand, so that the next to next work will be that two different ligand is influencing two process. One ligand which this influences better, another ligand which influences better. So the dual ligand is influencing rather than a single ligand. Single ligand can run into problem from substrate to substrate, but the dual ligand hopefully will be, I'll give you the clue that the bidentate ligand versus a monodentate ligand, this is what we are playing with, and it is giving the much better result. So again, all these are, I would say, circumstantial at this point of time, but once the full story is building, I think it will be much clearer. Okay, so the dual ligand, we believe this is the first story. First story has to be first story, but then there is subsequent stories to develop, and that's what we believe is going to be.
But as you draw it, it seems like that the iodide is forming the radical. That means it's reducing the iodide according to this cycle.
Right.
Okay.
But the things, and no matter what it is we do, it's much more complicated than what could be reflected in the slide.
Yeah, okay.
Thank you.
Perfect. Thank you.
Yeah, thank you very much for this interesting talk,
much.
Professor Maiti. I have the question related to this proteins or enzymes cavity where you are placing the metal ion and then performing the reaction. So as per my understanding, the proteins and enzymes, they tend to denature when there is some change in the temperature or pH or ionic strength or solvent or whatsoever. So how do you account such parameters change when you are performing such reactions? Can that be a limitation for such reactions? And how to address these challenges?
Yeah,
if they exist.
Absolutely. See, first of all, what you say is all those are correct, and we try to struggle with it. Anyone who is dealing with the protein and specifically trying to do the organic catalysis with the protein, this is a phenomenon every day one has to address. You can have aggregation, you have the denature, and you also have the solubility issue, which is for the organic reaction, it's a big deal. Partly we get away with this is because these are tetrameric streptavidin. These are almost like rock solid in a way. For the protein world, it is a rock solid. Protein is very delicate and very sensitive in terms of pH and temperature and everything. But the tetrameric streptavidin that we deal with, we are almost able to deal it as if like it's an organic reagent, not like protein. The sensitivity is much less compared to many other protein. So part of it is that it's not that sensitive. pH range also we can work. There is a good range or window where we can work on. So I would say that is giving us the opportunity or window of opportunity to operate. The temperature is also, as you can see, I didn't discuss much, the temperature can also be varied. It's a lot of protein will have trouble or will give you trouble, denature, and lots of other things can happen. But over here, it still stays good until a certain temperature, right? So both the temperature unit or temperature window as well as the pH window is little bit broader than many other enzymes. That's what we get away with many organic reaction that we try to do. Okay, that's the first thing. But nonetheless, this is a recurring problem. We have to deal with it, and the solubility. The good thing is this sort of reaction as well as the protein is okay to deal with. Even let's say acetonitrile or bit of this solvent, some of the solvent mixture, it still works. So semi-soluble, a little bit soluble, we still get the.
When there is some change in the pH or the solvent, then the microstructure of the protein or the enzyme is changing, and then could it lead to some other product?
Well, I would love to see that if by changing the structure by the means of temperature or pH, if there is orthogonal selectivity or some sort of cross selectivity for other product formation, that would be, I would say, good discovery. We didn't come across anything such, but we keep our eyes open to see if there is any unusual type of product formation.
Yeah, that would be interesting.
This will be the accident you would like to have or like to see. This serendipity, one day might will happen, but so far didn't happen. Yeah.
Okay, thank you.
Okay. So if there is no other question, please join me in thanking Professor Maiti again for his so wonderful talk. Now we have a tradition here, Professor Maiti, to felicitate our speaker.
Oh, wow.
I request our Dean Academic, Professor Aniruddha Chakraborty, to felicitate our speaker today.
Thank you.
That's
Great. Thanks. Yeah, I think I look like Pakka Himachal